guess I'll start my talk. Yeah, so I'm Tom Switzer. I'm just going to talk a bit about how we can use some concepts from abstract algebra in a programming context, and how I've done that and how it's useful. So I'm actually the co-author of a library called numeric programming library called Spire, along with Erica Scheim. So that's kind of a lot of the stuff I talk about. We'll actually be using examples from here, so it's a good thing to check out. Yeah, so I just want to start by just talking about my motivation for giving this talk. The main thing is I'm just seeing some of these concepts come up more often now. I mean, obviously in Spire itself, we have a little sub-package devoted to a bunch of type classes for abstract algebra. We also have a lot of other stuff, but I mean, it's kind of one of those packages I haven't really been able to talk about when I talk about Spire because, you know, I'm not speaking the same language as a lot of other people, so I want to get everybody versed in the language of these kind of concepts. I'm also seeing in a lot of other libraries like algebra from Twitter, which focus on large-scale analytics, and they have a lot of type classes for abstract algebra concepts and use them for big data, which is cool. Breeze is a library that's focused on NLP and machine learning, and they have a lot of this type of stuff as well. And there's also Basis, which is a library seen by Chris Sachs, which seems to just have a whole ton of nifty things in it. But he has some of these things as well, and I figure, you know, let's try to get the word out to the broader audience and try to get people all talking about the same thing. So my talk is actually just going to basically, I'm going to talk about a few of the basic ones. I'm going to talk about monoids, groups, rings, fields, and modules and vector spaces. And you'll learn what those are in a second. But I'm going to try to basically show each one with an example and try to hopefully convince you that these are abstractions you want to use through these examples. So I'm going to start by just saying that, you know, there's a lot of problems that, although they don't necessarily look like it at first, are actually algebraic. So we'll just talk about monoids because they're incredibly basic. Just a quick poll. Does everybody here know what a monoid is? Looks like almost all of you. That's awesome. Okay, so basically, it's really straightforward. You have some associative operation. You can apply to two types, A, and you get an A out. And you have an identity. And this identity basically means if you apply the identity on either side of the operation, you get back what the other value was. So you can kind of see that down there. Just as a notation point, the little operators you see, like that pipe plus pipe, that just comes from Spire. We had operators for all our type classes. So, I mean, you have the monoid, but you can just do a pipe plus pipe and you get your associative operator. So monoids are great just because there's just tons of them. I mean, a lot of things are basically associative. You just have to look hard enough. Obviously, the easiest ones are strings and lists. You can concatenate them. Your general concepts of numeric addition and multiplication. You know, you have an identity of 0 or 1, and you can add or multiply, and you get back the same thing, and it's associative. Pretty much any associative operation, you can just lift it up to an option. None becomes your identity, and so you got that as well. There's also a lot of fancy data structures. I think algebra probably has a bunch, and there's a talk today, which I imagine we'll talk about those things. Yeah, but why I want to talk about monoids is they're kind of interesting because they actually represent really, they're basically a well-behaved fold. So when you think about a fold, like as defined in Seq and Scala, you basically start with some element and then you can apply an operator f to all the elements and you get one out. So it reduces it down to a single element. And why I say well-behaved is fold doesn't promise that you're going to go from left to right or right to left. All it promises is that it's going to apply them in generally the right order. So I mean, in an associative order. So I'll have an example in a second. But basically, what fold really wants is just a monoid. So by abstracting that, what we're really talking about is a monoid is a good way to represent reduction. And we do that in our Precog code base. So to kind of give you an example, you know, you can go from the left to right, like fold left does. You can go from the right to left, like fold right does. Or you can split it up into two, compute them separately, possibly on different machines, and then combine them at the end. And as long as you maintain the proper sequence, you're good. Scala's parallel collections library, their fold actually requires this. However, it's left to you to make sure it happens. If you have a monoid, at least you know that's going to be correct. I don't want to talk about monoids too much because clearly most of you already know about them. I'm going to go on to groups. So a group is really just a monoid, but it adds this notion of symmetry. So you can always go back. You can get an inverse of something. So for everything, there's an opposite thing on the other side that lets you go back to where you started. And this is really cool because there's a lot of interesting examples. I mean, obviously you have your regular numeric stuff. But things like permutations, if you have a permutation, you can always get a reverse permutation. The Rubik's Cube, if you think about it like, if you're holding it, you have a rotation this way, you can always go back. And you can rotate all the way around. Or you can change the orientation of the Rubik's Cube. And if your operator is basically just concatenating these all together, then you actually generate a group, and you can always get an inverse for everything. So to give an example of a group, we're going to go with, we're going to talk about, have this catalog. And so the catalog is basically, we can add and remove items to the catalog. But the main thing is that we actually store in an append-only database. So we can never actually remove something from the database. We can only say what has happened. So it's much more, it's a more constrained problem. So anyways, our main goal is really to summarize the items in the catalog and be able to do that with this notion that you can't actually remove things. So basically, we'll start. We have this nice little catalog here. We basically have one method on it, reduce, which basically takes a monoid and will reduce the elements. However, it requires a function that maps a set of events. And so basically, our catalog is just a bunch of events. When we add something, we have to say we've added it. We remove something, we say we've removed it. We don't actually remove it, we just say what we did. And so we have this kind of notion of symmetry here, which we're going to try to exploit, where we can both add something and remove it. So if we're actually doing this with a monoid, say we wanted to count all the items in our catalog, then what we might do is, we have to give it this little map function that knows about events. And we basically have to say, well, if we're adding it, we'll add 1. If we're removing it, we'll take away 1. And then everything will work out. But we kind of have this notion of symmetry here, where we're either adding 1 or removing 1. But it's not very explicit. And so we have this monoid, but really you don't want a monoid. We really want something that can represent that. So we want a group. And so we're going to abstract over that symmetry, and we're going to, instead of taking a monoid, we're going to take a group. And what that lets us do is that we can instead just, our function that maps values from A to B, just only has to worry about A. It doesn't have to worry about this idea of adding or removing things. We can completely ignore the fact that this is an append-only database. The only thing is we have this slight restriction that it has to be a group instead of a monoid for a reduction. So if we wanted to count all the items in our list now, we can just basically say, reduce, and we just map it to 1. And this little method here will take care of the actual finding the inverse and everything. The operator at the end, that inverse just comes from Spire. So as a more concrete example, we'll look at a movie. So basically you have a movie which has a title and a length, and you have this catalog of movies. And so I'm just actually going to, hopefully this works, kind of show the example in here. So so we got our movies, and we have this reduce method. Basically what we want to do is we want to take a movie, and if we want to count it, for instance, but I think we could just say 1. And we're going to count up all our movies in our list. These movies are just generated randomly. I'll put the code up after the conference. But an interesting thing is, let's just say we wanted to find instead of finding the count of it, we wanted to find the mean. So what's the average length of all the movies, of the length of the movies, because we have that field available to us. So what I'm talking about is just direct products quickly. Yeah, that's a little unfortunate. Yeah, so anyways, if we wanted to get the average length, we can get the total length by basically just taking our movies and getting our length out. Sorry, I just gotta. So I'm just gonna get the additive group for double because doubles actually aren't. They have is ambiguous when you say groups. In Spire, you have to explicitly say that. What do you mean? So we can get the length, and we have our count from before. So we can just divide them and do that. However, we're doing 2 reductions over the movie set, which probably isn't optimal. But what's nice is we can use something called direct product. So direct products basically means that if we have a 2-tuple, or a 2-tuple of where each element comes from a group, then basically we can create a new group, and we just perform everything element-wise. So if you have oops. So if we have we can create a group out of this. Get back our group. We can see our zeros here. Oh, sorry. And if we're adding it, we just add the left side and the right side separately. And so we can use this in a reduction to actually generate. They go back a 2 tuple. So we've only done one reduction now, but we actually have back both the count and the sum, and now we can just actually do the reduction by itself, or we can just compute the mean by dividing them. Sweet, that worked. Okay, so I'm just gonna skip over this. Okay, so now I'm going to talk about actually just kind of creating your own groups as well. And so we'll talk about this idea of stats. So instead of wanting to get the mean length, we also want to get the standard deviation, maybe the count, everything. You know, we kind of want to do this. So basically what we have is this nice way of collecting stats. So if we have the sum, the square of the sums, or the sum of the squares of the elements in the list, and the count, then we can compute the mean, the variance, which is nice. You can see here we have a nice little constructor for just creating a stats out of a double, which basically has one item in it. And so we can create a group out of this. And I'm not going to get too far into this, but basically we can see here that we basically just have a direct product again with 3 things. So we just sum up each one separately. Our 0 is just the same zeros in all of them, and our inverse is just the inverse of each of them separately. So we can use this in our reduction. Sorry. You can have our thing. We can say. So we can reduce this and we get our stats and we get the mean. We can see here that the average movie length is 100 minutes, plus or minus 15 minutes is a good way to go. So anyways, yeah. Okay, so that's going to cover it for groups. But now I'm going to talk about the other thing that being precise, which abstract algebra lets us be very precise, is that we get to ask only for what we need. So I'll first just introduce the concept of a ring. A ring is just an abelian group. We have a notion of addition, which is an abelian group. Abelian just means it's commutative, so x plus y is the same as y plus x. We also have this notion of multiplication, which by itself is a monoid. However, we also have this idea of how these two operations interact with each other, and they're distributive. If remember, primary school, multiplication, you can if you have a times in brackets, x plus y, then that's just equal to a times x plus a times y. Very basic stuff, but that turns out to be a useful thing. So anyways, the main thing is that a ring is really a very basic notion of a number. The sort of canonical example is your set of integers, right? We can multiply, we can add them, we can't really divide them, so we just ignore that aspect of it. So Scala also has a kind of an idea about this where they have this type called numeric, and why this relates back to what I was saying about asking for what you need. The problem with numeric is that it requires a lot, so it's not just a ring. Like, this is how you would, for instance, define Scala's numeric in Scala, or in Spire. It's not just a ring, it also needs a notion of an ordering, it also needs to be signed, and not all rings are like that, and sometimes you don't want it to have to be constrained that way. And generally I find that if you have to put sys.errors or something like that in your implementation, or unsupported operation, it's a bad abstraction. So the main thing is I think we're asking too much. So to give an example of this, we're going to talk about convex hulls. So basically, technically it's the minimal convex set containing a set of points. However, the way you can think about this is if each of these points was instead a nail in a board, and we had an elastic, and we stretched our elastic around the points, and then we let it go. It would snap over and it would form this nice convex hull. Here you can see. And so to create a convex hull, we have a very simple algorithm. There's one called the gram scan. And the main thing is we basically sort the points lexicographically. So along the x-axis first, and then the y if they're equal. So we get this nice ordering. Then what we do is we build the hull iteratively from left to right. So we go one at a time. So we can go from 1 to 2, we got our hull, it's just that. We add 3 in there, we have a problem. So what we want our hull to do is to always turn left. As long as we're always turning left as we traverse it, we have a convex hull. So what we do is every time we see a right turn, we get rid of it. So we have a right turn, we get rid of it. we get rid of it. And you can see here we just iteratively, slowly build up this convex hull. And we get the lower hull here. We can reverse the points that do it again. We get the upper hull. It's a really nice algorithm. It's fast. It just requires sorting. It also requires a way to actually determine the turn of the points. So as we go from P to Q to R, we need to be able to figure out if we made a right turn or a left turn. So actually doing this turn is the sine of, it's proportional to, if we take the sine of the area of the triangle, but if we take the sine of that, then we actually get the turn. And so we're getting the orientation of the triangle. We take the sine of that, and we can get that. Because we don't actually need the exact value, we don't have to divide by 2 or anything. So what we can actually do instead is just use multiplication and subtraction. And as we know, that's just a ring. We don't need to have division here. So what that means is that we don't need to ask for anything more. We don't need to ask for Scala's idea of numeric or anything. We can just create our own with a ring, which is nice. So I'm going to give a quick demo of this. So I have a nice little way to generate points. I do believe I need a number. All right, so we're just going to generate a whole bunch of points here. And this is actually the hull. We'll get the size because it's things that you can see this. Anyway, so we get this, this convex hull here. What's kind of interesting is because we're only asked for a ring, we can also do it with integers as well. Oops. You get the convex hull of integers, which is kind of nifty. Obviously, it's a lot of big numbers. But what's other interesting is there's a lot of other neat examples of rings. One of them is the polynomials, the univariate polynomials, for instance, in an example I'll show you. So we can actually create our points as polynomial. And this is just a class I created for these examples. Just represents polynomials as a map. Addition of polynomials is just how you think about adding polynomials, and same with multiplication. It's very, very straightforward. So just create a few of these. Oops. Higher order one here. And so, our convex hull algorithm itself actually requires an ordering. So we can't find the convex hull of a set of polynomials, obviously. But we can find the turn. And we get back a polynomial. And what's cool about this is that, once again, because we didn't have to worry about the actual numeric type, we get back this thing. But it turns out that what we actually get is if you think about those 3 points as basically being points in motion described by that polynomial, and you can think about our variable being time, then what we get is a polynomial that describes the orientation of the triangle formed by those 3 points in time over time, which I think is pretty cool. So it opens up to things that you wouldn't even necessarily think are useful to you. So by asking for only what you need, you get to let users do what they want, really. So the other thing I'll talk about is this idea of basically just ignoring the details. So it does go back to what we had before, which is that by asking for what you want, like a ring, you don't need to actually worry about integers or doubles or anything else like that. You just worry about the basic properties of what you want. So we'll quickly mention fields. Fields basically add division to your rings. So the multiplication is now an abelian group. Once again, abelian just means it's commutative. And so in Spire, we actually just we define reciprocal in terms of div because most types are much better at defining div, but we'll see why. So fields are obviously useful because they add division. And so the sort of nice simple example of this is line intersection. So for intersecting lines, we represent lines as in the general form. And basically, we have a very simple way of getting the intersection of a line. Don't worry about the code too much. The important thing is that we have this division here at the end. And this division means that we need a field. But it also makes it kind of interesting because if we require just doubles, so basically doubles have division, then we'd have to worry about error rounds because now unless d is a power of 2, you're pretty much, the best you can do is an approximation to the actual intersection of that point, which may not be what you want. Maybe you want to have exact ones. So, if precision matters, then that's you don't want to lock yourself down to using a specific number type. On the other hand, if precision doesn't matter, you don't want to lock your user to using a really precise type. So if you don't care about it, you can just use double. If you do care, you can use something like rational, which is a number type in Spire. And it's not just a problem with floating point. We also have integer overflow. I mean, once again, if you by not tying yourself down to a particular type of number, if a user sees overflow, they can stick a big int in there instead, if it's a ring. Yeah. Okay. I'll also briefly talk about vector spaces. So we go back to our notion of groups. Turns out vectors are groups as well, is a group as well. So you can add vectors together and you can subtract them using exactly how you think it would happen. So vector space just basically adds this notion that we have the scalars, the scalars inside the scalars. Too much Scala. Inside the so the vector is basically made of a bunch of scalars. And the main thing is that we can distribute these. So if we if we have a vector addition, so here you have v plus w at the bottom, sorry for the people who can't see. Then we can multiply it by some scalar, and we can actually just, you have this nice law here. And in Spire, we have this idea of timesing from the left and the right. You don't need to worry about that. The main thing is we have this scalar multiplication, and we have it with a star colon. And we can also scale them. So to give an example, we'll do a catalog again. We'll see how this can be possibly use a vector space in a catalog, which seems a little crazy at first. But basically, so we have our same old catalog. We have this reduction with a monoid, and we have our events. Except we've added a new field to our events now. We have a count. So we aren't just adding one item. We're adding a bunch of items, or we're removing a bunch of items from our catalog. Of course, groups still work. If we see that we have n things we want to multiply together, or n things we're adding together, we can just fill with our n times and then fold over that. Obviously, that's not very efficient. So to solve our problem, we're going to actually look at modules. I'm just going to introduce this very quickly. A module is basically a vector space, but we generalize the scalars to only lie in a ring, so we don't need division. You do lose a lot in terms of, it doesn't necessarily have a basis, but for us, that's not too important. But the nice thing is that basically we have like v plus v plus v plus v. We can return that into a 5 times v. So basically, if we wanted to reduce with modules, what we can do instead is basically we take another function that just maps a to b, and instead now we just use this scalar multiplication to handle the counts itself. So to give an example, I have, call that. All right, so we have this new thing called an inventory. Oops. And so the inventory is basically a bunch of products here. And so this is kind of terrible, but basically the products, the main thing is the products have this idea of volume. And so basically we just want to get our volume. And so as it turns out, using our new reduce function, we can actually just take our product and we can put in a stats. And so our statistics is actually a vector space. I should actually parse that then. So we actually define the module here. I actually defined it as a vector space. It's also a group, so that's why the other example worked. But the main thing is we actually get back this thing, and once again, we can just get the mean of the volume and all that other stuff. So anyways, I think that's interesting. And so this is all we wanted to go over. I think there's a lot of interesting examples, more or less. I think we have to wrap it up. So I'm just going to talk about some more information. So all the examples in this use Spire. So if you're interested in any of this stuff, I would suggest checking it out. There's an example subproject that has a lot of cool examples. For instance, one of the reasons why, for instance, ring, we don't have an idea of equality with rings is one of the examples is the endomorphism ring. So if you take a group, all the endomorphisms from that group to itself, which is just a homomorphism from a type to its same type. You can form a group by doing plus, the addition is doing this, we apply the endomorphism, and we add the two together at the end. And multiplication is composition. And what's really cool is if we actually do the endomorphism group over integers, we actually get back a group ring that's isomorphic to the integers, which is nifty. Ring of integers, obviously. Also other ones, for vector spaces, there's some nifty examples for k-means and random forest. Erica Scheim also has an example of this idea of clean closure, which I don't quite understand, but it's really awesome. It does a whole bunch of stuff. But it's definitely worth checking out. If you want to learn a bit more about abstract algebra, there's the first link there is actually a set of, it's kind of a book / lecture notes by a guy, and it's free, so it's a good resource. It's also a book I like, Algebra by Arden, but I mean, that's your kind of deal. So I'm going to open the floor to questions.